On behalf of the Geo-Institute Board of Governors, I'd like to welcome you all to this conference. And I think we have a lot of great activities that would be of interest to you all. We are going to be having a number of technical sessions. We have the three major lectures during this conference. And then we have the student activities, and as I indicated to some people last night, go to those student activities. If you want to be reinvigorated about the great profession that we serve in, just watch it in the students and you'll come away even more invigorated and enthused about the profession that we've grown to love. I'd also like to thank the other organizers that are cooperating with the Geo-Institute and the organization of this conference, NAGS, IF, AI, and GMA. We really appreciate the opportunity of working together with other organizations in the geosynthetics area, which have a huge impact on geotechnical engineering. So we certainly appreciate this opportunity to team with them during this conference. In keeping with what I did last night with the seed lecture, I'd like to give you a little bit of a primer to this distinguished lecture and share with you some insightful quotes from the man this lecture is named after, Dr. Ralph Peck. These quotes here were extracted from an interview of Dr. Peck in the summer 2004 issue of Deep Foundations, published by DFI. The question was posed to Dr. Peck: design build trends in the U.S., good for the industry or bad for the industry? Dr. Peck's response was, I think good. It makes designers conscious of the construction aspects. Engineers got into the habit of designing and not concerning themselves with how it's going to be constructed. I think this is really key when it comes to designing structures, knowing or trying to look at it from the contractor's perspective and see how it's actually going to be put together and become a reality. He goes on to say, my first real job was on the Chicago subway and had very little contact with the designers. I was working with Terzaghi, who was working for the city of Chicago. I was his man on the job. We first made borings and soil tests and then began to measure what was going on in the field. So the question came to him, the birth of the observational method? His response was, for me it was. He had one more question I thought was worthwhile considering. What do you consider to be today's problems? And Dr. Peck's response was, in engineering, there's too much emphasis in engineering education on computer solutions. The computer is a wonderful gadget. You can analyze things you couldn't before, but it's still a machine. It has to be operated and interpreted by something of intelligence. I thought that was a good, insightful quote. I have several other quotes as well that were extracted from Professor Ralph Peck's Legacy website. On the area of designs, he said this: simple calculations based on a range of variables are better than elaborate ones based on limited input. Another one, he said, sophisticated calculation is too often substituted for painstaking subsurface investigation. The ease for the fascination of carrying out calculations, taking into account complex loadings, geometrics, and soil conditions leads many of us to believe that realistic results will somehow emerge even if vital subsurface characteristics are undetected, ignored, or oversimplified. On construction, he said this: in my view, nobody can be a good designer, a good researcher, a leader in the civil engineering profession unless he understands the methods and the problems of the builder. On observation and instrumentation, he said this: instrumentation is no substitute for adequate design. Pretty simple concept, but I think it is pretty powerful, it's pretty profound. He also said this: "What is often forgotten is that the observational method is an adjunct to design, not a substitute for it." And then finally he said this, and I really like this statement. He said, "An instrument too often overlooked in our technical world is a human eye connected to the brain of an intelligent human being." So in other words, we really need to be thinking about what we're doing and then putting it into practice and coming up with good designs. So in that light, it is a pleasure to participate in the prestigious Ralph B. Peck Award lecture. The award was established in 1999 by the Geo-Institute in honor of Dr. Ralph Peck. The Ralph B. Peck Award is presented for outstanding contributions to the geotechnical engineering profession through the publication of a thoughtful, carefully researched case history or histories, or the publication of recommended practices or design methodologies based on the evaluation of case histories. The 2011 Peck Lecture is Professor Antonio Bobet, Associate Director for Research, Global Engineering Program, Purdue University. Dr. Bobet received his Doctor of Science degree in Civil Engineering from Massachusetts Institute of Technology in 1997 after completing a 6-year degree program equivalent to a bachelor and master's at a university in Madrid, Spain with honors. After joining Purdue University in 1997 as an assistant professor, Dr. Bobet was a research assistant in the Department of Civil and Environmental Engineering at Massachusetts Institute of Technology. Prior to that, from 1994 to 1992, Dr. Bobet worked for 2 construction firms, first as a project engineer and then as a construction manager. He has several honors and awards, including the 2005 Roy E. and Myrna Wanzik Research Award in 2005 at the School of Civil Engineering at Purdue University, and he is the chair of the 46th U.S. Rock Mechanics Symposium in 2012. Further, Dr. Bobet has a number of publications to his credit. Professor Bobet is one of the leading researchers in the field of rock mechanics, seismic loading, and engineering geosciences, consistent with the example set by Ralph Peck and other distinguished recipients of this award. I'd like to ask Professor Bobet to join me here on the podium. Professor Bobet, in recognition for your extensive contributions to the geotechnical knowledge in the field of rock mechanics, seismic loading, and engineering geosciences case histories, I would like to present you with this medal and award. Congratulations.
Good morning. Thank you very much to the Geo-Institute for this award. And it's an honor to receive the Peck lecture. Peck is one of the greatest engineers of our profession, and for me particularly it's very humbling to receive this honor. I'm going to go directly to the presentation, and I'll try to work maybe with the mouse to highlight some of the aspects, so hopefully that will work. The focus or the topic of this presentation is what we learned after the failure of the Daikai station. And the Daikai station is relevant because this is really the first underground structure that collapsed during an earthquake and is well instrumented, and there was no liquefaction. But before starting, I would like to share with you a couple of quotes from Dr. Peck that I find relevant for this presentation. The first one is that says, "The most fruitful research grows out of practical problems." The second one is translating the findings of our research into simple concepts and procedures for the guidance of the practicing engineer is, in my opinion, a duty and worthy activity of our profession. So I hope that these two quotes that inspired some of us to move forward with this research are going to be, or you are going to find them relevant to this presentation. The work could not have been done without the help of many people. And I want to acknowledge them right now. One is Dr. Huo, who is now at Earth Sciences, geotechnical engineer, very good colleague, Gabe Fernandez at the University of Illinois, and colleagues in structures, because we were looking at the failure of a structure, underground structure. And to work on that, we need the expertise of different disciplines. And we work together, geotech and structures, and I hope that you'll agree with me that that was a fruitful collaboration. So I want to acknowledge the work of our colleagues in structures, Dr. Ramirez at Purdue, Dr. Sozen, also at Purdue, Dr. Para Montesinos at the University of Michigan, and Dr. Maekawa at the University of Tokyo, and also the support of NSF and Purdue University. This is the outline of the presentation. I'm going to start with motivation of the work, a little bit of background, then I want to spend a few minutes about our current design, and maybe highlight the problems that I see what we are doing right now. Then get a little bit into the details about the work that we did, what are the results that we got, some of the conclusions, get into the lessons that we think we learned, and then I would like to move forward and propose an approach for design of underground structures, and finish up with some conclusions. What you see here is two pictures that hopefully bring the setup of what is happening. This is the epicenter of the Kobe earthquake in 1995. What you see here is the epicenters of the earthquakes that occurred between 1961 to 1994 with different intensities. This was an earthquake with an intensity of 6.9. The epicenter was about 13 kilometers deep, about 15 kilometers from the city of Kobe. The source, of course, of these earthquakes, by the way, the Friday earthquake with an 8.9 magnitude, that was where pretty much the epicenter happened. This is a very large earthquake, a great loss to Japan, and I hope that today we should all have our thoughts with the Japanese, with our colleagues over there at this time of great trial. The source for the earthquake, on the right-hand side, you see this picture is the movement of the Pacific Sea Plate and the Philippine Sea Plate and the Pacific Plate that are moving against the Eurasian Plate and the North American Plate. You have these troughs and these contacts, and this is a source of these large earthquakes. The picture that you have on the left-hand side, that's this yellow star. You don't see, I'm not sure that you see the... All right. This is the epicenter, this is this yellow star, the epicenter of the earthquake, and then what you see is the aftershocks after the earthquake, and the lines are contours of equal acceleration as it was spreading from the epicenter at the aftershocks of the earthquake. Maximum peak ground acceleration of about 0.84 Gs. The picture that you have on the right-hand side is a contour of the intensity of the earthquake, and this red zone is of intensity between 9 and 11. And as you move away from the epicenter of the earthquake, you expect that the intensity would decrease, and indeed does so. And away from the epicenter, you see these blue contours with intensities. This is the modified Mercalli intensity, less than 5. Of course, as you move away, you expect a decrease of intensity, but also as you move away, the soil conditions change. Close to the Osaka Bay, you have soft soils, and that provides a significant amplification of the earthquake. As you move away, there are two issues that play a role. One is the distance, of course, and also the ground conditions change. You get into a rock, and then the ground motions are a little bit lower. This sketch tries to provide a little bit of a summary of the damage that was produced during the earthquake. The two islands that you see there, Port Island and Rocco Island, these are artificial islands. There was significant liquefaction. At the bottom left of the picture, you see the epicenter of the earthquake. Then you move towards the city of Kobe, which is about 15 kilometers from the epicenter. There was significant destruction. There was about 5,500 people who died because of the earthquake, about 180,000 buildings that collapsed, significant fires after the earthquake that caused also a lot of damage, and that's because of the loss of lifelines. The Kobe station was very close to this node that says Sanomiya. That's where the focus of this talk is going to be. These are two photographs of the road 28, that's road 28 on top of the Daikai station that shows the subsidence on the top, and that's caused by the collapse of the station, about 200 meters long by 20 meters wide, about 2.5 meters of settlement of the road. And what you see in this picture is the cross-section of the Daikai station. The top shows the collapse, and the bottom shows the original Daikai station, the cross-section. It was a reinforced concrete structure. It's a box-type structure. It was about 17 meters wide by 7 meters tall. It's about 4.8 meters below the surface. It was built between 1962 and 1964 by the cut and cover method, reinforced concrete, fairly thick walls, about 85 centimeters thick, and the station is supported by central columns, and we'll talk about the central columns a little bit later on, about 0.4 by 1 meter in dimensions, spaced about 3.5 meters. The failure of the Daikai station was because the central columns collapsed in shear. Is it a type of brittle failure? And the collapse of the central columns induced the collapse of the top slab of the station, and that created the subsidence of the road on top of the station. Now, the failure of the Daikai station is or at that point when we started our work was well known. It was, the station failed because it was not designed for seismic loading. And the collapse was by shear failure of the central columns, and as I said, that produced the collapse of the top slab. The work that we did, and the point that I'll try to make through this presentation, is that we were not necessarily interested in the collapse mechanism per se. What we wanted to find out and to investigate is the load transfer mechanisms between the surrounding soil and the structure. To identify these mechanisms, to understand what happens, and then maybe later on provide some guidelines for the design of these stations. What I show here is pictures of the inside of the station. What you see here is the central columns that failed. The top is the top slab that collapsed as the columns failed. Now, if you could, let's focus on the top right picture, and you see the column that failed, and you can see all the longitudinal reinforcement of these columns. And you see how this longitudinal reinforcement buckled, and the core, the concrete of the core of the column is crushed. This is a typical mechanism of failure in shear, where there is not enough reinforcement, transverse reinforcement to absorb the shear forces induced by the earthquake. So the mechanism of the structural, if you will, mechanism of failure it was clear. Work done by others, by Maekawa and others, was nicely done and showed that the mechanism of failure was shear. But again, the point that we were trying to look at is how the soil and the structure work together, and how the displacements of the soil are transferred to the structure, and how the structure reacts. This is a plan view of the failure of the station. The top is, as I mentioned, the plan view is about 30 columns that collapse, about 100 meters long. The bottom is a vertical cross-section of the station with the columns collapsed. We'll talk later on that there are 3 areas of the station that we want to look at. One is the areas that collapsed and the others that did not. And then the question would be why this area or this cross-section or structure collapsed and the others didn't. This is a plan view, is a sketch of the Kobe underground rapid system. This red circle shows where the Daikai station is located. Kobe has 2 underground transport systems. One is a public transport system, the other one is a private transport system. The Daikai station belongs to the private transport system, but the other names that appear here, Sanomiya, Kanizawa, Nagata, Shin Nagata, these are names of the stations that also suffered damage. And as I move through the presentation, one of the points I'll try to make, and I'll insist about this later on, is that underground structures are sensitive to seismic loading. And that I think that issue has been somewhat disregarded by us and by our colleagues in structures. This is a sketch of the underground rapid transit system in Kobe. The Daikai station is in red, that's where the collapse occurred. If you look on the left-hand side, there is the Kosaku Nagata station. There was damage there too, 5 columns, and the end of the station was damaged. The tunnel communicating the Kosaku Nagata station with the Daikai station, 210 columns were damaged. As I mentioned, the Daikai station collapsed. If you move towards the right to the Shinkaichi underground station, next to this station there was an underground shopping mall with also damage to the structures. So if we move into current design, there are 3 sources of damage to underground structures. One is fault displacement, ground failure, and ground shaking. Fault displacement causes damage because the underground structure crosses an active fault. There is displacement of the active fault, and then this displacement either has to be accommodated by the surrounding ground, by the support, or there is going to be damage to whatever is inside of the underground structure. So what I show here is a mine in Israel where there was a relative movement between the 2 sides of this mine of about 45 centimeters. Ground failure can be produced typically by portal failure, slope failure at the portals of the tunnel, but also could be produced by liquefaction around the structure, also by landslides, and depending on how the soil fails, the impact on the underground structure might be mostly in tension, like is shown on the top picture, or it can be in tension and bending, as it shows on the bottom figure, or the other source could be ground shaking, which is the type of damage that that occurred in the Daikai station. And that's the one that I'm going to be focused on this presentation. Now, on the following slides, let's see if I can make the point that indeed underground structures are sensitive to seismic loading. What I'm showing here is 2 plots. One on the left-hand side is a plot from Dowding in 1977. He compiled about 71 case histories of tunnels that suffered damage during an earthquake. So on the horizontal axis, you have the number, the case number. On the vertical axis is the peak acceleration. This is the acceleration that is measured on the surface on top of the center of the tunnel. Of the 71 tunnels, about 20% of those, the type of damage was classified as significant damage. These are the dots that are black. There were 2 other types of damage. One is minor damage or light damage. These are the gray dots, and no damage, that's the white dots. He provided a recommendation or a conclusion that says, well, you know, if you, the peak ground acceleration on top of the tunnel is less than 0.2 Gs, then the tunnel is not going to have damage. If the acceleration is larger than about 0.5 Gs, then the damage to the underground structures can be significant, and moderate to light damage if the peak ground acceleration is between 0.2 and 0.5 Gs. Sherman Judd, in 1991, they look at about 190 tunnels, and they look at the level of damage. They classify the damage again into moderate to high. This is the black columns, slight damage, this is the gray, and none, that would be the white. And they provide a little bit more an insight into the sources, the causes of damage, looking at different factors that might affect damage to the tunnels. And I'm presenting two. There were others that they looked into. One is the overburden. This is the top picture on the horizontal axis. You have the overburden. And the numbers may be a little bit smaller for this room, but it increases the overburden from left to right. And I hope that you agree with me that if you look at the column most on the left of this top graph, you have a significant percentage of tunnels that are damaged, and this is for low overburden. So one of the conclusions that we could come up with after this plot is that tunnels that are closer to the surface are more sensitive to earthquakes. But we have to be a little bit careful about this conclusion, because the tunnels that are closer to the surface are maybe built by cut and cover, so the cross section is going to be rectangular, and rectangular cross sections are indeed more sensitive to earthquakes than circular cross sections. And also the tunnels that are going to be closer to the surface may be excavated in ground conditions, in soils that are softer than in tunnels that are excavated at depth, and thus they may be exposed to higher displacements. The bottom figure, what shows is the classification of the damage depending on the type of surrounding ground. And on the vertical axis is the number of cases. So the column on the far right, this represents the tunnels that are excavated in what is here called colluvium, which is soil, and the other columns represent rock. So if you think in terms of stiffness, and we'll talk about stiffness a little bit more later on, the tunnels that are excavated in softer ground, initially they seem to be more sensitive to damage than tunnels that are excavated in stiffer materials. This is a similar classification that was done after the Chi-Chi earthquake in Taiwan in 1999. What you have in the vertical axis is the number of cases. What you have on the horizontal axis is the damage location. And one of the tunnels crossed an active fault. There was damage at the portals, mostly in terms of landslides and slope failure, and damage to the tunnel itself by shaking. Huang looked at 57 cases. Of these 57 cases, 49 show damage to the tunnels. So I hope that I'm making the point that there is a significant evidence out there of damage to underground structures. So underground structures are, as I mentioned, sensitive to earthquakes, and we have to look at their response during an earthquake, and they have to be designed to resist the deformations imposed by the earthquake. Some illustrations about the damage that can occur in these underground structures. This is a mountain tunnel. It's a tunnel excavated in rock in Kobe after the earthquake. And the pictures show some of the damage that was found at the invert of the tunnel. That would be the bottom left picture, and some of the damage observed at the liner of the tunnel, at the spring line, for example, where there was spalling and buckling of the steel reinforcement. This is damage that occurred at the Longxi tunnel after the Wenchuan earthquake in 2008. The top left picture shows the failure at the portals. This, as I mentioned, this is typically in the form of slope failure, landslides. The other pictures show damage inside of the tunnel. And this is failure of the liner in compression, in shear, or in bending, and can lead to the collapse of the tunnel itself. And that's the picture, the bottom right picture. Now, when we design for underground structures, there are two scenarios that need to be considered. One is, of course, the static loading, and the other one is the deformations imposed by the earthquake. This is what I call here the static and the dynamic loading. The deformations induced by the earthquake, if I'm looking at let's say, a deep tunnel, are produced by the deformation waves that travel through the ground. And we have two types. One is P wave, where the deformations are produced along the direction of propagation of the wave. And the other one are shear waves, where the deformations are produced perpendicular to the direction of travel of the waves. P waves are depicted on the top figure, and shear waves are depicted at the bottom figure. Now, these waves are going to impinge the tunnel at general direction, but what we do, or we can do, is decompose these waves into waves that are P waves, that are parallel to the axis of the tunnel, and P waves that are perpendicular to the axis of the tunnel, and by shear waves that propagate parallel to the axis of the tunnel, and shear waves that propagate perpendicular to the axis of the tunnel. And each waves are going to induce different deformations on the tunnel itself. These are the deformations that we can expect on a tunnel when it's subjected to deformations due to shaking. On the top left, what you have is the deformations produced by P waves that are traveling parallel to the axis of the tunnel. But the deformations are in the form of compression and tension on the liner along the longitudinal direction. If the P waves are traveling perpendicular to the cross-section, this would be the picture on the top right. What you have is a compression of the cross-section of the tunnel. Shear waves that are propagating parallel to the axis of the tunnel, that would be the center left, and are propagating, let's say, on a vertical plane, that would produce bending deformations of the tunnel. That's what we call snaking deformations of the tunnel. Shear waves that are propagating perpendicular to the axis of the tunnel, but the direction of motion is along the axis of the tunnel. That is depicted on the center picture on the right-hand side, and what you have is shear deformations on top and bottom of the tunnel. The worst conditions by far are produced by shear waves that are propagating perpendicular to the axis of the tunnel, with motions also perpendicular to the axis of the tunnel. This is what is shown on the bottom of the figure. If you have a circular cross-section, that induces ovaling deformations of the tunnel, and it's a rectangular cross-section that produces what we call racking deformations of the tunnel. Again, these are the deformations that induce the larger strains on the tunnels compared to the other deformations. So these deformations need to be absorbed by the support of the tunnel or by the liner of the tunnel. And what you have on the left-hand side are the strains induced in the liner. They're going to have tangential strains. They are going to have axial strains and shear deformations, or shear strains, or deformations in the form of what is depicted on the right-hand side of the picture. Now, how are these deformations, the deformations induced by shear waves that are traveling perpendicular to the axis of the tunnel, and they have motions perpendicular to the axis of the tunnel? Most of the times, what is used is what is called the free field method. And the free field method, what it does is assumes that the structure deforms the same as the free field. Okay, so we compute the deformations of the free field, and then we say, well, we look at the location of the structure compared to these deformations, and we look at the difference in deformations between the top and bottom of the structure. That's the distortion of the structure. That's what we design the structure for. This is what is called the free field method. So we design the structure as if the structure is not there. Now, one of the other ways, or similar to the free field, is to use the equation that you see in the middle of this slide. That is an estimate of the shear deformation of the structure, which is the ratio of the peak particle velocity induced by the earthquake divided by the shear wave velocity of the medium. Now, this equation is based on elasticity. And of course, the deformations of the soil are going to be much larger than those induced by elasticity, but then if we try to estimate the deformations induced in the soil. They can be very large, and then we are in trouble trying to design a structure that is going to resist so much deformation. So it seems that the numbers that come up from this equation make sense, so then we use it most of the time. Okay, so that's what we do. But now let's think about what we do. So now I want to share with you a thought experiment. And the beauty of thought experiments is that we can do whatever we want. And we can come up with any scenario that is physically impossible, and yet we can think about that. So let's think about a very stiff tunnel. Okay, we put this stiff rectangular structure in an infinite medium, and then we impose far-field deformations in the form of far-field shear stresses or far-field shear strains. Now, what we expect is that far from the structure, we are going to recover free-field deformations. That's the principle of Saint-Venant, right? If we look far away from whatever point of application or disturbance that we have, what we recover should be independent of what is happening at this particular location. But what happens close to the structure? The structure is stiff. It's not going to deform. Of course, it's going to take some load because it's not going to deform. But also, the soil around the structure is not going to deform. So the structure is going to deform less than the free field. So if we use the free field method to design the structure, we are going to be maybe extremely conservative. Now, let's go to the other extreme, and that's why it's a thought experiment. Let's suppose that we introduce into this medium what we call a soft tunnel. Let's think of a hole, and it's a thought experiment because we don't have to think about the support of this hole. Let's do the same thing. We apply a far field deformation. Far from this hole, we're going to recover free field deformations. But now, because we have a hole, we have weakened this medium. Now, the deformations around this structure are going to be larger than the free field. So the design using the free field method in this case is non-conservative. So if we use the free field method for stiff structures, we are conservative, but we don't know by how much. If our structure is softer than the surrounding ground, then we are unconservative. So if there are two things that you can take from this lecture are that one is that we need to design underground structures for seismic design because they get damaged and they fail. And the second thing is that I think that the free field method should be abandoned because it provides very poor information about the actual response of the structure. Now, let's elaborate on this a little bit more. What I have here is the distortions introduced into a tunnel. It's a circular tunnel in an infinite medium subjected to two types of deformation. On the top is a P wave, at the bottom is a shear wave, and the solution of this deformation that you have on the right-hand side is based on elasticity. Yes, our geomaterials do not behave elastically, but I think that we cannot underestimate the power of closed-form solutions, even though the assumptions are going to be too restrictive, because with just looking at the solution from these equations, we can have a very quick idea of what is happening, understand the process, and also, very importantly, identify the variables that are important for our problem. So, yes, this is an elastic solution, and what I'm showing you on the right-hand side is the distortion of the cross-section on the top by a P wave and at the bottom by a shear wave. And if you look at the structure of this solution, what you have on the right-hand side of these two equations, two factors. The factor on the far right is the ratio of the peak particle velocity divided by the shear wave velocity. And I showed you before, and this is one of the equations that we use to estimate the deformations of the ground structures. But the factor in between, that's a factor that provides the interaction between the structure and the ground. And this factor has been derived with the condition that the compressibility of this liner is 0. That means that the length, there is no compression or extension of the length of the liner. But then one of the factors that you see in this central factor is this value of F. And we use it to denote flexibility, or more appropriately, the relative flexibility between the structure and the surrounding ground. And yes, it's an elastic solution, and then you have the Poisson ratio, but if you look at the definition of this factor F, which is in the middle, it provides a ratio between the stiffness of the soil and the stiffness of the structure. So if we take this factor and you make it 0, you have a stiff structure, and indeed you have 0 deformations. But if you have this factor and you make it infinite, right? This is a thought experiment, so we can do that. Then you have a very flexible structure, and then these ratios of deformation are going to be much, much larger, can be much larger than the ratio of peak particle velocity divided by P, or shear wave velocity. I hope that this slide closes this argument. You have 3 scenarios here. The one on the left is a medium where the structure has exactly the same flexibility than the surrounding ground. Then the deformations of the structure are going to be those of the surrounding ground. Now, the central one is a structure that is very stiff. The deformations are going to be 0. On the far right, on the right hand side, what you have is the deformations of a hole in an elastic medium. But if you look at the top, at the elastic solution, that delta R over R is a measure of the distortion of the structure. And that can be about 3 to 4 times larger than the distortion induced in the structure if the flexibility is the same as the surrounding ground. So again, still we use the free field method. The free field method actually was used for the redesign of the Daikai station. But the point I'm trying to make here is that that should be abandoned. Now, let me get a little bit into the details of the work that we did and what we learned. Of course, part of what I told you already is what we learned, so it's not a continuous process. But let me share with you some of the results that we get. So I'm going to get into the numerical analysis. I showed you this picture before. This is the plan view of the Daikai station and the vertical cross-section of the Daikai station. But there are here 3 distinct sections that this structure had. Section 1 is the one that collapsed. Section 2 is the tunnels that communicate stations. And section 3 is the access station. All these are different structures. All of them show different behavior. If we had used the free field method, all of them should have deformed the same, and yet the behavior is different. And the question, of course, is why. So these are the 3 sections. Section 1 is the one that collapsed. It's about 17 meters wide, 7 meters tall, about 4.8 meters below the surface. Section 2 is the tunnel. About 9 meters wide, 6 meters tall, same overburden. Section 1 has columns that I think the cross-section is 0.4 by 1, spaced at 3.5 meters. Section 2, the columns are a little bit smaller, 0.4 by 0.6 meters, spaced 2.5 meters. And section 3 is very large. This is the access station. It has about 26 meters wide and about 10 meters tall and reaches the surface. These are pictures of the station as it is today. And what you see is the central columns, these columns that are painted white and red. Everything is new except the bottom slab. The bottom slab is the original slab. The rest is rebuilt. So they excavated the station, they rebuilt the station, and they refilled the material around the station. Now, what you see on these columns, red and white, these are steel casings around the structure that provide additional ductility of the columns. That's a picture on the left-hand side of the end of the Daikai station. That's the transition from the station to the tunnel. And the picture on the right is a picture of the tunnels between stations. And you see the columns that are white and red, these are new, they didn't survive. The columns on the tunnel, they were damaged, but they survived the earthquake. And I think you see that on the right picture, that you see water at the bottom of the tunnel. The tunnel acts as a drain of the water surrounding the tunnel, and maybe that's one of the reasons why there was no liquefaction, because the water table was lowered because of the station from the original conditions. So what we did is numerical analysis. We discretized the medium. We put the station, each of the sections, section 1, section 2, section 3. We input the seismic motions at the bottom of the discretization. We used the actual soil properties at the site to do the simulations. Again, the point is to understand how the structure and the soil work together, not necessarily to reproduce the failure of the station. This picture shows the two investigations, soil investigations that were done for the station. The one on the left was done in 1959 for the design of the underground station. The one on the right was done after the failure of the station in 1995. This is an expanded view of the stratigraphy that was reported after this investigation. There are, in essence, like three types of soil. There is a fill on the top, about 1 to 2 meters thick. Then there are some soft deposits of Holocene origin, mostly fine sands and clays, low SPT blow counts, maybe between 8 and maybe up to 10 or maybe a little bit more. And then as you go deep, the origin of the deposits changes. They are of Pleistocene origin, also sands and clays, but they are much stiffer, with blow counts below a depth of about 20-something meters that go beyond 40 and 50. This picture shows the location of the acceleration that we use for the simulations. The picture on the left shows in red the location of the Daikai station, and in blue the vertical array of accelerometers that was placed at Port Island. Port Island, there was significant liquefaction. That was an artificial island, and with loose soil deposits on top, and that was the source of the liquefaction. The picture on the right shows the stratigraphy of Port Island, but I want to call your attention to the bottom of this figure, where you see these Pleistocene and gravel deposits, which are the same deposits that appear at the Daikai station. So it's the same geologic layer on the two sides, and that's understandable because, after all, the distance between the Daikai station and Port Island, I think it's about 3 kilometers. And that's the accelerometer that we use for our simulations. These are the accelerations, horizontal and vertical accelerations, that were registered at this location, at this depth, and these are the ones that we used in our simulations because this is the same soil layer that appears under the Daikai station. One point, we use both in our simulations. One point that I want to try to make right away is that in this particular case, the vertical acceleration, the influence on distortion of the structure was very small. The vertical accelerations, pretty much what it did was increase by about 16%. It's about 0.16 G. The vertical acceleration was increased by about 16%, the axial loads on the structural elements. We understood that one of the key factors that we needed to take into consideration to simulate the behavior of the structure was the relative stiffness between the structure and the surrounding ground. So we decided to use a soil model that was, on the one hand, simple enough so we could do all these simulations in a few days, and also robust enough such that we could get a solution.
but also that should represent the behavior of the soil. So it's a model that reflects the loss of stiffness of the soil with deformation, and also is a model that reflects the increase in damping of the soil with deformation. We check this model by making the comparisons between predictions from this model and laboratory results. So here you have a plot. On the left vertical axis is a plot of the shear stiffness degradation with shear strain, which is on the vertical axis. And on the vertical right axis, what you have is the damping ratio with respect to the maximum damping ratio. The solid dots are results from experiments. The continuous lines are the model, so we were happy that the results were quite good. We were doing a 2D analysis, and of course there is the question of the central columns. In a 2D, the central column is a wall, and yet is a column that is spaced. So what we did was simulations where we would change the stiffness of the central wall. The 2D is on top and the 3D is at the bottom. We would change the stiffness of the central wall such that the response, the behavior of the structure in 2D was equal to the response of the structure in 3D. Again, all this was done to capture the change of stiffness of the structure with respect to the surrounding soil, because this indeed, and I'll show you in a minute, is the most important factor that controls the deformations of underground structures. So going quickly through the results, this is a plot of the distortions of the central column of the structure that collapsed. That's the section 1 of the Daikai station. On the vertical axis, you have the column distortion, which is the difference in horizontal displacement between the top and bottom of the column. And on the horizontal axis, what you have is the time. Now, the maximum distortion was about 4 centimeters, and I'll explain in a minute. We'll go through the details and see if that indeed was enough for the collapse of the structure. Anything that is after 4 centimeters, it's basically theoretical because the structure was not there anymore. But yet we felt that we should go for times we should get the complete solution, because then we might learn something from it. And we did. So you look at this plot, of course you have a significant damping because of the soil model that we are using, but one of the things that is interesting is that at the end of the earthquake, about 20-25 seconds, you have, there are permanent displacements. So the displacements, they don't go back to zero. And this is because the loading and unloading portions of our soil model are not the same, and because of that, you expect to have some permanent distortions on the structure. Numerical methods have the advantage that you can get all solutions possible anywhere you want. The key, as mentioned earlier, is how to interpret these results, and I hope that we try to do some interpretation, and I hope I can share it with you. On the bottom, you have 3 plots here. The plot on the bottom is the same plot as before. That's the distortion of the column. And on the top, on the left, what you have is the axial force on the column with time, and on the right is the axial force on the lateral walls. And the axial force in the column, we wanted to get this plot because we wanted to do some structural calculations based on the strength of the concrete, based on the longitudinal reinforcement, based on the transverse reinforcement, and see if the results that we're getting from this model were consistent with the type of failure that was observed. But if you look at the plot on the left, you start from static conditions, and then you have the oscillations produced by the earthquake. But at the end result is that there is some unloading on the central column. But of course, if some part unloads, there is no free lunch. Somebody else has to take this load. And if you look at the plot on the right, indeed, the lateral walls are the ones that take the load. And that is not uncommon on underground structures, because the center of the structure is going to be a little bit more flexible than the edges of the structure. So the center tries to unload, there is some arching effect, and it transfers a little bit of load from the center part of the structure to the stiffer lateral walls of the structure. Shear forces on the top left and moments, both are connected by a factor because there is no load acting on the column. I'll get to these plots of the shear, a little bit more discussion in a minute. Now, if you look at the deformations of the 3 sections of the station, so the 2 plots on the top correspond to section 1 and section 2. The top left is section 1, the right is section 2, the bottom is section 3. And if you focus, just for the sake of it, the discussion between section 1, which is the station that collapsed, and section 2, which is the tunnel. And I'm focusing on these 2 because they have the same dimension, so it's easy to think and compare those 2. So you look at these 2, the deformations of section 1 are larger than those of section 2. The deformations of section 1 are about 4 centimeters, that's what the model predicts, while the deformations of section 2 are 3 centimeters. The reason for that, and the soil around the structure, of course, is the same. The reason for that is that section 1 is a little bit more flexible than section 2. And because of that, it's going to deform, it deforms more than section 2. Now, if you look at the distribution of axial forces and shear forces, which are the forces that, again, we need for the structural analysis, in red you have section 1, and in blue you have section 2, the tunnel. Section 1 has larger axial forces because the span of the station is larger, and also has larger shear forces because the span is larger and deforms more than section 2. This is, I'm going to get a little bit into the details of structural analysis, and I think this is important because as geotechs, we need to understand what our colleagues in the structures do, and perhaps more importantly, we need to convince our colleagues in the structures that they need to understand what we in geotech do. In here, I'm showing a picture on the top of the collapse of the column, the central column of station 1. At the bottom is the same picture I showed you before of the tunnel between the stations. On the right-hand side, what you have is a picture of the steel reinforcement of section 1 and section 2. The top is section 1. It was heavily reinforced in the axial direction. It had like 6% of the area was steel. The transverse reinforcement was done by hoops and by zigzag stirrups that were kind of connecting these columns. But if you look at the spacing on the far right of this picture, the spacing was 350 millimeters. If you look at our current code for the spacing of a transverse reinforcement is about 100 millimeters. So clearly the spacing was too large. These stirrups and this transverse reinforcement could not prevent the buckling of the longitudinal reinforcement. And if you look at the actual picture, you see this longitudinal reinforcement that is buckling. It's because there is a lack of a transverse reinforcement. The bottom, on the right-hand side bottom, shows the steel reinforcement on column on the central column of the tunnel, and you have longitudinal reinforcement of about 1.6, much light axial reinforcement, and you have transverse reinforcement, and the spacing is closer, it's about 200 millimeters. We did some detailed calculations of the response of the 2 columns, the column of section 1 and column section 2. I'm showing here just the results of column 1. So the plot on the left shows the shear demand. That's the shear that needs to be applied to the central column for a particular drift. That's on the horizontal axis. The drift is the difference in horizontal displacement between the top and bottom of the column divided by the height of the column. And what you see in red is a couple of cycles, the last cycles of deformation of the central column. And we did some of these cycles for different axial loads between 4,000 and 5,000 kilonewtons, which were the axial loads predicted by the model. And this, actually, this is a model that we use for nonlinear response of concrete. But the model showed that failure of the column in shear would have occurred at about 1.05, 1.1%, which is the actual drift demand. That's the deformation imposed by the earthquake. And that would require the column to support about 620 kilonewtons, and the shear capacity of the column was only about 80% of the demand. And, of course, then column 1 failed. Column 2, because it had smaller axial load, it had smaller reinforcement, axial longitudinal reinforcement, and it had a better distribution of transverse reinforcement that survived. At least our calculation showed that it should survive the earthquake. Now, to highlight the importance of the relative stiffness, how the relative stiffness between the structure and the soil influenced the results, we did a number of calculations, and this one just showed what happens on the column distortion when we change the stiffness of the structure. And what we did was just change the Young's modulus of the structure. The blue plot shows the plot that I showed you before. And the red shows the deformations if we increase the stiffness of the structure by an order of magnitude. The red shows what happens to the structure if we decrease the stiffness of the structure by an order of magnitude. And I hope that you see that by changing, well, this is a significant change in stiffness of the structure with respect to the soil, then the distortions induced on the structure are significant. I said that it looks like an order of magnitude is significant, but when we talk about soils, changes of a factor of 2, 5 or so with strain are not uncommon, and so it is when we have reinforced concrete structures. When there is damage, we see drops in the stiffness of the structure of a factor of 2 or 3 easily. Now, we wanted to look at what happens, how the structure responds to the soil, and how the soil, most importantly, responds to the presence of the structure. So what I'm showing here is 3 plots, each one for each of the sections of the station. Section 1 on the top left, section 2 top right, section 3 at the bottom. And these lines in red, these are contours of the ratio of the stiffness of the soil divided by G maximum, the small scale stiffness of the soil. And these contours are plotted at the point, at the moment when there is maximum distortion of the structure. Okay? So these are contour plots of the actual stiffness of the structure, of the soil, at the point of maximum distortion of the structure, normalized by the initial stiffness of the soil, which, if you can think, also is a magnitude and a measure of the deformations of the soil, because the soil stiffness degrades with deformation. Now, if you look at these contours, as you move away from the structure, let's focus on section 1 for a minute. So as you move away from the structure, you move from the top right corner to the bottom left corner, you begin to see values that are of the order of 0.4, 0.3, which means that the soil recovers the free field. As you get closer to the structure, these values of the normalized shear deformation of the soil increase to 0.8 to 0.9 and higher. So that means that there is a volume of soil, we call it a volume of soil attached to the structure. There is a volume of soil that is attached to the structure that moves with the structure, because the Daikai structure, this section 1, section 2, and section 3 are stiffer than the surrounding ground. What happens is that this structure constrains the deformations of the surrounding ground, so the ground around the structure does not deform as much as the free field. And that it's a concept that I'm going to use in a few minutes to propose simple or simplified way of estimating the deformations of underground structures. The size of this volume of soil attached to the structure depends on the dimension of the structure, but also depends on the stiffness of the structure. Depends on another factor, which is interface between the structure and the surrounding soil, and we'll talk about this in a minute. So, if you look at the interface, okay, we go back to this plot. We can think about relative stiffness. Relative stiffness is the most important factor that controls deformation. But if we think in terms of relative stiffness, the soil has a potential to impose deformation on the structure. The soil deforms. By the way, underground structures, this is a deformation-based problem rather than a stress-based problem. So we have these potential of the soil to impose a deformation on the structure. And this potential is going to be modified by the relative stiffness between the structure and the surrounding ground. In this particular case, because the structure is stiffer than the surrounding soil, but I also show you a case where the structure was softer than the surrounding soil. Now, this potential has to be imposed on the structure through the interface. And through the interface, we are going to be able to transfer normal stresses, and we're going to be able to transfer shear stresses. So if we look at what is the expectation? If we have a very stiff interface, let's suppose that we are thinking about a tight interface. That means that the soil can transfer as much shear to the structure as needed. The expectation would be that the stiffer or the stronger the contact, the larger the deformation of the structure. And indeed, if you look at this plot on the vertical axis shows the distortion of a structure with a frictional interface normalized by the distortion of a structure with a tight interface. And the horizontal axis, what we have is the coefficient of friction between at the interface between the soil and the structure. Now, if you look at this plot, and the results are obtained for different ratios of the width to height of the structure. But you look at this plot, what we see is that as the coefficient of friction increases, the deformations of the structure increases, and then they end up for a coefficient of friction for this particular case for about 1.4 or so, we recover a tight interface. So yes, that plot shows that as you have a stronger interface, the deformation of the structure are larger. We do these calculations again with the soil model, nonlinear soil model, the structure, so on and so forth. And now I'm showing you 3 plots. The plot on the top left is with a frictional interface of 0.4. And by the way, we did all the calculations I showed you before were done with this frictional interface. It's an interface that as there is relative slip between the soil and the structure, you have friction that is controlled by this coefficient of friction, and the soil can detach from the structure. All these plots are for the section of the station that collapsed. On the top right, what you have is the structure distortion, the column distortion, when the coefficient of friction is 0. On the bottom, what you have is the distortions of the station when the interface is tight. Okay? Now, if we look at the distortion that is produced, what we see is that the larger distortions are produced by coefficient of friction of 0.4, then by a tight interface, and the smallest ones are when there is no interface. Okay. And yet, the concept that we have is that a tight interface should produce more displacement. So what's happening here? So we go back to our plot of contours on how to see how the soil reacts in the presence of the structure with the 3 interfaces. So the contour plots on the top left are the ones I showed you before with a frictional interface. On the top right is with a frictionless interface. There is no shear that can be transmitted from the soil to the structure. And the bottom is with a tight interface. Now we look at this volume of soil attached to the structure and the size, you see that this size is related with the interface. Why so? You look at the bottom, the tight interface, the volume of soil attached to the structure is very large. And it's very large because the structure constrains significantly the soil because the shear at the interface is significant. The plot on the top right, this volume of attached soil is very small because the constraints of the soil, because the constraints of the structure on the soil are much smaller. The soil around the structure can deform more because there is no shear at the interface. So there are 2 factors here that kind of play together, but they go in opposite direction. One is the relative stiffness. That's the potential for the soil to induce deformation on the structure. But the other one is the capability of the soil to induce this deformation on the structure. And that depends on the interface. So while a strong interface, what produces is a strong capabilities of inducing deformation of the structure, the potential is smaller because it constrains the soil more. A weak interface, it has a low capabilities of inducing deformations because there is no shear. Only the deformations can only be transmitted with normal stresses. And yet the deformations on the soil are going to be larger because it's less constrained. So the potential to induce deformations are larger. Of the two factors, the one that controls by far the deformation of the structure is the relative stiffness. So, what are the lessons learned, at least some of them? One is that, of course, the design of the Daikai station was not adequate because it was not designed for seismic deformations, that the deformations depend strongly on relative stiffness, that interface friction has an effect on the deformation of the structure, and we just talked about how a stiff structure deforms compared to the soil or a soft structure, on what are the effects of the interface. But let me go back again to the 2 points that right now I want to remind all of us. One is that underground structures are sensitive to earthquake loading and must be designed. They need to be designed to resist earthquake loading. And second is that the free field method should be abandoned, and we should incorporate into our design the effects, the presence of the structure. All these calculations were done on a university environment where we have access to good computational resources. We were able to write our own model. These simulations on a large computer took a few days. All this is great and possible. The question is, what about practitioners? Maybe not everybody has access to the resources that we have, and what we do with what we have learned, and what are the recommendations that we could make to practitioners. So the key is that we need practical, simple, and yet accurate solutions that can be used by practitioners. So it would be great if we could, instead of doing dynamic analysis, we could do static analysis that incorporate shear modulus degradation, and maybe we can think of some equivalent linear analysis. Then what happens with interface effects, because it's easier to think in terms of a tight contact rather than a frictional contact, and also what happens with depth as different structures, maybe they are close to the surface and we go with depth. There is quite a bit of work that has done out there that shows, and here I'm showing some recommendations from Hendron and Gabe Fernandez, that shows that if the wavelength of the ground motions is about 8 times or larger, effective of significant cross-section of the structure, then a pseudostatic analysis, a static analysis is okay. So what I'm going to do is follow the discussion for putting forward a simple and accurate, I would say, method for practice. I'm going to focus on a deep structure. It's a deep rectangular structure subjected to far field shear stresses or strains induced by the earthquake in the free field. And it has dimensions, A for width, B for height. And I'm showing here a plot of relative deformations on the vertical axis. What you see is the structure deformations normalized by the free field deformation. So we know the free field deformations of the medium of the soil. We go to this plot and we can get the deformations of the structure. On the horizontal axis, what I have here is a factor F, which is a measure of the relative flexibility between the structure and the surrounding ground, and you can think of as a measure of what is the stiffness of the structure compared to the stiffness of the surrounding ground. There are 2 sets of data here. One is generated by Wang in 1993 for different flexibility ratios. That was done on using actual earthquakes. It's a dynamic analysis. And the other one, all these gray circles, are static analyses with structures with the same flexibility. And you see that the data match very well. So unless the structure is very close to the source of the earthquake, and we are dealing with significant frequency, very high frequencies, the static or quasi-static analysis will work well. We also developed an analytical solution. We wanted to have also some charts that could be used to come up with structure deformations. Here is a plot for different shapes of rectangular structures, from square to rectangular structures. On the vertical axis, you have the normalized structure deformation. On the horizontal axis, you have the relative flexibility or relative stiffness between the structure and the surrounding ground. So you know the two of those, you can have an estimate of the deformation of the structure. All this, of course, is done with the assumption that everything is elastic. For the structure, it's okay, because we want to design structures that are going to sustain little damage. So the behavior of the structure is going to be mostly within the elastic regime. But what happens with the soil, right? The soil is going to go significant deformations, and that is not captured by any of the two plots that I show you. Analytical solutions have the advantage that once you know the deformations, you know everything, so you can have an estimate of the pressures and shear distribution of the structure. You can do structural calculations. But if we go back to the concept of this volume of attached soil around the structure, and the soil deforms with the structure, then we can think of a kind of an iterative scheme where let's think that we start with a stiffness of the soil to do our calculations. We do either a finite element method, assuming elasticity, or we go to these charts. We find the deformations of the structure. The soil around the structure is going to deform the same as the structure. So once I know the deformations of the structure, I know the deformations of the soil. I can go to a chart of a shear modulus degradation of the soil with respect to shear deformations, and I can compute what would have been the stiffness of the soil. If this stiffness of the soil is the same as the stiffness that I used to start the calculations, that's the end of the process. If it's not, that means that the initial assumption was not correct. We need to modify the stiffness of the soil. So we can attempt a second iteration using as the stiffness of the second calculation, the stiffness that results at the end of the first calculation. So we go through an iterative loop where we use as input of the stiffness of the soil estimated from the last iteration. So we do that, and here I show you a comparison between the distortions of the three sections of the Daikai station. You have a column with this nonlinear dynamic model, and another column with this analytical solution with the iteration process. And you see that differences are fairly small, certainly acceptable with the uncertainty that we have when we deal with seismic loading. We thought we should go outside the range of cases that we looked at to estimate or to validate or verify the approach. So here what we did is look at the LA Civic Center station with the Northridge earthquake, where you have a schematic of the soil at the site. We input accelerations obtained from the Glendale Las Palmas station, 0.36 G horizontal, 0.13 G vertical. You have on the right-hand side, you have the distortions of the central column. This is a plot or a table with all the results with the three Daikais and the LA, and you see that the predictions are acceptable. So this is an iterative process. What happens with interface, because we are using a tight interface, and if we look at this plot, the expectation is that we are going to be, the approach that we are proposing is going to be about 10-15% on the conservative side if we use an interface that is tight, that is frictional. If we look at what happens at depth, the deeper the structure, the larger the deformation. So if you look at this plot on the vertical axis, it has a normalized distortion of the structure compared to the distortion of a deep structure. And on the horizontal axis, what you have is a measure of the overburden. So for overburden of about 1.5, which means that is the ratio of overburden over the height of the structure can be considered deep. So deep structures are going to have about, following this plot, about 50%, maybe 20% larger deformations than shallow structure. So if we do our calculations and we assume that the interface is tight, we should be 10-15% on the conservative side. If we do our calculations with a deep structure, we should be, again, 15, maybe 20% on the conservative side. There is a factor that is not included here, which is the effect that I showed you before, that a frictional interface produces a decrease in the stiffness of the soil, and then that produces an increase in the deformations of the structure. This effect that is not considered here is on the unsafe side by about 15 to 20%. So we have factors that are compensating factors, and we estimate that the error that we should get following this approach is of the order of 15 to 20%, which again, I think that for the level of uncertainty should be acceptable. So the errors, as I mentioned, are of the order of 10-15%. That would be an approach that should be okay for a preliminary design or for routine structures. But perhaps most importantly, what we need to do is provide additional ductility to our structures such that brittle failures are prevented. And probably that would be the most important thought through the design process because of all the uncertainties associated with this thought. Now, there is a scenario that I think has not been explored as much as it should, which is what happens with structures that are below the water table, where excess pore pressures may be produced. I'm not talking about liquefaction, because if there is liquefaction, probably what we would do is densify the soil before building the structure. What I'm talking about is that once the structure is there is not going to be liquefaction, but excess pore pressures may be generated. What we do with these structures, so that we know very little about that, and I think that that's something that we should consider. I would like to finish this talk with two quotes from Dr. Peck, and that are, I think, relevant to what I discussed. One says that no theory can be considered satisfactory until it has been adequately checked by actual observations. And the second one is that the most successful practitioners of the art of engineering will maintain a healthy respect for the ability of nature to produce surprises. And with that, I'd like to conclude my talk and thank you, all of you, for your kind attention. Thank you very much.